we're very fortunate to have Stephanie Noble here. You heard from her already at the careers panel, so you've heard a little bit about her sort of path and so on. And Stephanie's been involved in developing this kind of ecosystem, super interesting tools to do data analysis in the web browser, and she'll tell us all about that. Thanks.
All right. Well, thank you all for coming today to kind of hang out with me. So you've heard a lot of people talk about whether or not there's some issues with reproducibility in the field. In 2016, there was this survey done by an editor at Nature that asked scientists across biomedicine whether they thought there were some issues with reproducibility, if not a full-blown crisis. And the majority of respondents thought that there were at least some issues. I know a lot of people have issues with this term, like a reproducibility crisis, but let's say that there seemed to be a large amount of agreement that there are at least some problems. And there are a number of solutions that have been proposed to deal with this. And this has been proposed across a number of different fields. So from the government side, we see the NIH unveiling plans to enhance reproducibility in their funded work. So if you've written NIH grants, you may have had to talk about, rigor and reproducibility in those grants. Company context like Amgen has also talked about raising standards in, let's say, preclinical research. And we've seen across the field of neuroscience, this talk about issues with power and reproducibility and how this is really an endemic problem that doesn't just face neuroimaging, but the field of neuroscience more broadly. I will say we've been talking about this quite a bit, specifically in neuroimaging. And as I've been talking to some of you about before, this is a field that's really used to having some of our most fundamental methods be questioned from the beginning. So I think that we're a field that's really good at trying to think about issues like reproducibility and open science and solutions from the beginning. But one common theme across many of these proposed solutions is a need for analytical methods that will lead to more precise inference. So typically, when we're talking about precision in psychology, we're referring to these two different cornerstones of accurate measurements. And that's reliability, or the ability to get repeated similar results given repeated trials, and validity, which is the extent to which a measure might correspond with a desired outcome. So if we have this bullet, here I'll just actually move, I'll select OK on the closed captioning. All right. So if we have this target, and what we're desiring is for someone to hit the bullseye on this target, and we let them shoot, and they shoot in this pattern, we can see that the arrows are pretty well clustered together. This is an example of a reliable shot. However, it's fairly far from the center of the bullseye. In contrast, if we saw a pattern of shots like this, we might say, we're not quite hitting the bullseye, and the arrows aren't really clustered either. So it doesn't seem very reliable. But if you actually took the average kind of in Euclidean distance of all these arrows together, this would converge upon the bullseye. And if we had millions of shots like this, the average would get closer and closer to the bullseye. So in that sense, this might actually have more validity than the previous case, even though it's less reliable. And both of these things are critically important. We want to be able to have a pretty precise shot on every single shot. We want to get close to the bullseye. But also, if it's all clustered together and it's very, all the shots are really close to one another, but they're very far from the bullseye, that's not very useful either. So both of these things are really important. I often talk quite a bit about test-retest reliability in many of my talks, and also at the Utah Statistics Conference, if people are ever interested in that. Today, I'm actually going to focus a little bit less on that, but I did want to point you towards a guide that I wrote to sort of orient you towards some of these concepts as they're commonly used in the field, including drawing from some of my own experiences. And also I wanted to point out Alex, who's a researcher in my lab, a PhD student, who's kind of our subcortical detective, digging deeper into these questions of why is subcortical test-retest reliability so low, tends to be much lower than all of our other brain areas that we measure, and what might we be able to do about it. But so today we're going to move past reliability and focus a little bit more on validity, on the correspondence with a desired outcome. And typically when I'm talking about validity, I'm talking about this common goal of measuring the validity of our inferential methods that we tend to use, with the standard goal of trying to find true positives and minimize false positives. So let's dig a little more into that. So there's a lot of discussion about specifically improving power in fMRI. And this is often through the lens of trying to improve reproducibility, as we were talking about before. So you might have seen a number of these papers, people talking about improving power by getting adequate sample sizes, or more powerful study designs, better inferential procedures, or more reliable and valid measures. But as great as these are, as signposts pointing in the right direction, these actually lead to a number of other open questions that we need to answer. We're saying, we need a lot more data. We need higher sample sizes. Some people are suggesting on the order of thousands of individuals. Some people are suggesting actually we should gather larger scan durations as well. So within subject ends. And what exactly is the answer? Do we need thousands of individuals? Can many labs afford thousands of individuals? It might not be possible. So there are open questions like that. There have been different kind of focuses on whether we should use power analyses or other sorts of procedures to design our studies, maybe designing to yield a specified level of accuracy of our estimated effects. But there are a number of other questions like this. To answer these questions productively requires us to have a power estimator that's specifically tailored for fMRI, because fMRI has very complex data structure, and it also has really complex inferential procedures for which standard parametric inferential approaches do not work for estimating power. And this might seem pretty easy because there are so many power calculators out there, but actually this is very difficult in the context of our field. So I'm going to talk about a path toward better estimation of effect sizes and subsequently power for fMRI study planning. And this is kind of part one of the talk. We're going to get into the ecosystem of tools for analyzing studies in part two. So part one of this path towards better estimation of effects is actually just understand what sort of effects we might expect for typical study designs. Seems like something that would already have existed out there, but it's also very hard to gather the requisite amount of data to estimate these sorts of effects and to put them together in kind of a way that could be meaningful. So that's step one. And step two is to develop a tailored power estimation procedure specifically for some of these typical studies that people might care a lot about. So I'll focus first on step one. So how we define typical studies here, just as a starting point, generalizability is limited to specific studies, but the idea is first we could start with these typical studies that might be helpful for people as a starting point for designing their own studies in the future. So here a study refers to an analysis used to estimate the effect of a unique phenomenon in a given data set. So a specific data set might have multiple studies in the way that we're defining it. The criteria is we're looking for studies that have more than 400 subjects. And also we're looking for things that reflect very typical study designs that we might find in the field. And that's a little bit more subjective. And it also depends on what's actually readily available at that sample size. So we start with 6 data sets: HBN, PNC, SLIM, HCP, ABCD, and the UK Biobank. And these reflect 4 different sample sizes. This is just kind of a Sankey plot that's sort of organizing what each of these studies that we're using, what categories they all fall into. So we have 4 sample sizes. We're pretty well represented by the 1,500, 1,000 sample size area. We have 2 different brain mapping types. One is task-based activation, and the other is functional connectivity. And we have 3 effect types. One is kind of a group contrast, so T2, t-test sort of type. And then there's a standard, like within sample t-statistic, t-test sort of situation. And then there's a correlation, just sort of a normal brain behavior, brain phenotype correlation. I'll talk a little bit more about this in a second, but you can think of the correlation context as being related to the 2 sample t-test context. And then we're looking at 5 different outcome categories. So we have cognitive things, we have tasks, we have demographic information, psychiatric information, and biometric. So altogether, for now, we have 45 studies. Actually, we have a little bit more than are shown here. And so we have 45 different unique effect maps that we can have in our repository. So I want to talk a little bit about how we're going to standardize the way we estimate effect sizes so we can compare across all these different contrasts. So there are a couple of ways that we can select an effect size. I think 2 of the most popular would be a Cohen's d or an R squared. Here we're working with Cohen's d. That seems a little bit more something that people are talking about at the moment in the field. So we can easily use some standardized conversions to go from T or correlation to Cohen's d. I want to point out, actually, there's this standard conversion from correlation to Cohen's d that people tend to use. A friend of mine, Maya Mather, was talking a little bit more recently about how we tend to make this implicit assumption when we use that standard conversion that we're sort of breaking the data set into something where the x-axis is where we're looking at a difference in two standard deviations in the x-axis. And then we're looking at the corresponding difference in the y variable that corresponds to those two standard deviations distance. And you can change that, you don't have to stick with that. It's a pretty, you might think that it's a sort of arbitrary decision, but it's a very common decision. But you should feel free to, reorganize that as you would find interesting. So we're using these very standard conversions to Cohen's d. And I also want to point out that even though this is kind of a starting place, there's actually quite different implications for using Cohen's d for within subject analyses versus between subject analyses. So one example is, if we look at the standard small, medium, large Cohen's d, the sample size that we would need to detect a effect with 80% power for a within subject design is actually half the amount of the sample size that we would need to detect that same effect size using a between subject design. So already you can see that we're not comparing directly, like the implications of the same effect size is not exactly the same across the within and between subject designs. So that's just something that's pretty important to keep in mind. So I'm going to show you guys some of these exemplar maps of effect sizes, along with some 95% confidence intervals, simultaneous confidence intervals. And this is a little bit different than a standard confidence interval for a single point estimate. The difference here is that you can think of this as akin to a Bonferroni correction. So what you're looking for is that you have 95% of experiments, if you did infinite number of experiments, would contain the true value of your estimate for all edges and voxels. But let's say 5 out of 100 experiments, or really 5% of infinite experiments, you might not have the correct value in all of those intervals. So we're trying to control the proportion of effect size, the proportion of times that the effect size is in all intervals simultaneously. So in practice, what that looks like is instead of estimating a normal confidence interval, you kind of make that a little bigger. So here's some representative studies from the HCP. Here's a between subject design. So we're looking at a correlation between resting functional connectivity and age. So this is akin to what people are calling brain-wide association studies or brain behavior associations. In this context, looking at the simultaneous confidence intervals, I actually paint in blue those areas where the confidence intervals overlap with 0. So that means that an effect size could be 0. It could be anything in those intervals, but also if you were to take the most conservative estimate of what an effect could possibly be, that it could be 0. So here in some of these contexts, using the HCP, on the order of 1,000 subjects, we actually find that the majority of effects could be 0, at least with the amount of precision we're able to measure. When we do a group contrast, so here I'm showing, people who are reported as biologically male versus biologically female, just doing a 2-sample t-test here, we find that, a few more effects might not be 0, but 80% of the effects could possibly be 0. We can look in contrast to the within subject designs. So here I have a task contrast between functional connectivity during a working memory task and functional connectivity at rest. And in this context, we find that 30% of effects could actually be 0. But the other parts of this simultaneous confidence interval are not overlapping with 0. So even our most conservative estimate of those effects would actually not be 0. And then finally, for task-based activation, it's interesting because I think that people have had some different hypotheses about where this would go. Task-based activation, we're doing a truly highly intensive within subject design. But we find actually that more effects could be 0. But still, you can see the within subject context compared to the between subject context, we tend to have more, presumably conservative estimates of non-zero effects. But here's kind of a sort of takeaway from these exemplar studies. Functional connectivity tends to be a little bit higher than task-based activation when we're doing within subject analyses. And then just a group contrast versus a group contrast and correlation tend to be a little bit more similar, but you get somewhat larger effects when doing group contrasts. So those are just a few exemplar studies, and we can actually pull this out and see what happened in all the other studies that we were looking at in this database. And I'll say that we see pretty, similar effects across all these studies. The UK Biobank, which is on the order of 40,000 subjects, that's quite different. We have more precision to detect those effects. So that's one piece where you'll see that these equals might not overlap, but they are very small effects that we can detect in the UK Biobank, even with age or fluid intelligence, things that are often used as benchmark phenotypes or biometric variables. So I would say just sort of a quick recap here. To be most conservative, I would recommend planning for effects to be at the between subject level, quite small, very small, and it's possible, at least with these largest data sets that we have, that the majority of effects could be very close to zero. I'll say that psychological constructs happen to be the most difficult to detect in the studies that we've been looking at. And the maximum conservative effect size across all of the between subject contexts, across all of these studies, has been less than medium. So the very, very maximum single edge or voxel is less than medium. In contrast, if you're doing a within subject study, you might plan for effects to be more modest or medium. There is a substantial number of non-zero effects, and the maximum conservative potency that we observed across all of these is actually quite large, and especially for functional connectivity. And to put this another way, to think of this a little bit pragmatically, if you were lucky enough to be measuring a part of the brain that had the very largest effect size of everything that we observed in all of these studies, just very lucky, just to know out of all these 100,000 voxels, I'm picking that voxel, or out of all these 30,000 edges, I'm picking that one edge, and I'm just doing inference there. The number of subjects that we would need to detect that effect with 80% power would be about 400 subjects for the correlation context, or about 70 subjects for the group contrast. But you can see, you can actually detect this effect with maybe 4 or 5 subjects for the within subject designs. All right, so that was a lot of an overview of what we found from these studies, and I'd like to talk a little bit about the Shiny app that we've been developing. It's a bit cut off, but there's Hallie's face over there, and she's actually going to introduce you all to this app.
Okay. Hello, everyone. I'm Hallie. For those of you that I haven't met, but luckily I have met a lot of you so far, so that's nice. This is the Shiny app that we have made to show all of this effect size data. And I'm just going to briefly walk you through it, and then I'll show you how it works a little bit. So in the middle, we have those same plots that Steph was just showing you, except I just realized we use different colors. So red for me is the bad ones in the middle, and green are the good ones. But that's the same thing that Steph was showing. So when you open the app, we have all of those down the middle for all of the studies that we have, that I think are closer to like 70 now. Then on the left, you have ways to filter through those, because since there's so many, not all of them are relevant to what you want to be looking for. So you can use these things on the left to filter it down and just show what you're interested in. Then on the right, you can see in more detail where these effects are located, because sure, there might be some really large effects that you could power yourself to detect, but we don't know where they are unless you look on the right-hand side. Then you can tell better off where they are. So you can look at them on a functional connectivity matrix for the FC studies, and then you can also look lower down at the activation maps for those studies. And you can click through, I'll show you afterwards. If you have multiple studies showing up that meet your criteria, then on the right-hand side with the matrix, it's just showing an average over those. And you can also download the data. So if you want to be even more specific about a certain brain region or a network that you're interested in, you can download these effect maps and then apply any sort of mask or parcellation that you might have to locate that better. And you can also contribute your data to this, which I'll talk about more afterwards. But that is how we can get some more data sets for it. So it'll be a growing resource. So even if there's not data sets that match what you're interested in now, there might be later. Okay, so I'm gonna go to it there, and I hope this doesn't break it. And
there's that QR code I was sort of cut off out there, but feel free to follow along. You can follow along on your phone or on your computer if you'd like to.
okay,
Otherwise, you can go to the Neuroprism website.
we can go Neuroprism Lab Shiny app. See you later. No, hang on, let me go to the Neuroprism Lab website. Everything pops up automatically on my laptop because I go to it so often. Okay, there it is. That's another way you can get to it. Okay. We will put this like this, and it'll load. And as it loads, this is a good time to mention that this is a work in progress, still updating it as we go. And that being said, though, very open to feedback if you use it. Okay. Give it one more second. And it'll update. There we go. Okay, so here's all the maps down the middle. Is that big enough? Yeah. Okay. And if you scroll down, you can see there's a lot of them. So you can go on the left-hand side here and filter. Maybe you're interested in a certain task you can go to, and it will update and show you what we have that meets just that. It will update very soon. Hopefully. Oh no, maybe because so many people are on it. We've never tested that out. Okay, good to know. Well,
Thank you.
it might kick some other people off, but okay. Anyways, while that loads, that's okay. Actually, you can explore it yourself. We'll just go back to this. And it doesn't, yeah, it's kind of self-explanatory. You can follow the instructions on the side if it doesn't make sense, or come find me later and we can talk about it more. Anyways, then I'm going to talk a little bit about the structure of the Shiny app as well. Raise of hands, who's heard of a Shiny app before? Steph? Okay, good. Anybody made one before? Nice, a few. Okay. So for this data, we started out and need it's all coming from contributors. And so we get this data from other people at the subject level, and we need to figure out a way to organize that in a standardized way, which fits well with what a lot of people have been talking about this week. Steph and I have come up with this way on the right-hand side of organizing the data that people send us, and we can talk about that more later if people are interested in it, but I don't want to bore those who are not interested in it. But we've been thinking a lot about the naming. So people will give us the data in this structure, and then we run it through a script that we have that calculates the effect maps and with and without different motion regression and pooled or unpooled data, all these different iterations of it. And we get the data that gets fed into the Shiny app. So then we get to the app, and the Shiny apps are basically built in two parts. So you have a user interface script and a server script. And the user interface tells you like where to put everything. And you can say, I want a drop down over here, and I want a plot in the middle, and I want a plot over here. And then the server script goes and tells it how to populate those different areas. And then it in that references the data. So we have a data directory where we store all of those effect maps and also any other data we need for the plotting, that sort of thing. And then we also have a script with the various helper functions that we need. We're working through this to try to modularize it and make it cleaner as we go. once it's looking better, we'll have that, the script for everything also up on GitHub when people go to the Shiny app. And I think that's all I have, so it's back to Steph.
Oh, right.
Thank you, Hallie. Yeah, Hallie's been awesome, thinking really carefully. We've been having many different conversations about how to best organize this to prepare for more contribution, because we think that something like this will really only be useful if we have a contribution of lots of different study types from lots of different people. There are, of course, a number of different studies that we're missing. Task-based activations, it would be great if we had more large data set task-based activations, more clinical variables across a number of different contexts, more developmental information as well would be really great. But yeah, and I thank you, Hallie, that was fantastic. All right, so here we are. We have this platform, this beginning repository, where we're characterizing what sort of effect sizes we might expect for typical designs. So the next step from there is to develop that tailored power estimation procedure and another Shiny app that allows us to estimate power for typical studies that you might be able to use to generalize to your own studies. So there are several historical power calculators that exist specifically for fMRI. Unfortunately, they are no longer available. Some of them have sort of aged out. But it's been a really great first step to try to understand what ballpark of number of subjects you might need to properly power your studies. These tend to be more estimating power for parametric inferential procedures like random field theory, or let's say just a single univariate test, a single univariate linear test. I'm proposing here a new approach, which I'm sort of just generally calling an empirical benchmarking approach to power calculation. You can see some of my thoughts on this approach in this paper that we published in PNAS, talking about looking at larger scales of inference and how we can improve power by using some differential inferential approaches that leverage wide scale dependence. So I talk a little bit more about, error estimation and how we use some subsampling of larger data sets to try to estimate things like power. But you can estimate many other things in addition to power, many other types of error. I'd say there are several pros to this approach. One is that there's no requirement for a user to provide a map of user-defined effect sizes. There are certainly pros and cons to this approach. So one big pro is that the type of data that a user typically has from their own study is pilot data that is typically very small n. So your ability to estimate an accurate effect size from that very small n data is quite poor. And then there's the double dipping scenario where you're using a subset of the data of your overall study to estimate your power for that study. And you kind of are pretending like these are two separate data sets, but they're really not. So there's some circularity issues there too. That is a very typical way of doing a power analysis, is to use pilot small n data. And I would say everything has its pros and cons, but it's just important to be aware of that particular limitation. Another pro of this procedure here is that since we're using this resampling approach and estimating errors directly from our data, this is actually adaptable to arbitrarily complex inferential procedures. So not just random field theory, cluster-based inference, but non-parametric cluster-based inference based on permutation testing, or any other sort of complex procedure that you could possibly think of, maybe new procedures that we probably haven't even heard of yet, maybe some multivariate procedures for which it would be really hard to specify theoretically the behavior of that procedure. This can just be adapted for that, as long as you can define a ground truth and your error estimation for that ground truth. We've given a lot of thought to certain large-scale pooling and cluster-level inference and univariate error estimation procedures. So please check out that paper, and specifically the supplemental information of that paper, where I lay out all this different, error estimation stuff. And then a final pro of this approach is that it's actually very easy to use. It'll be just like what Hallie showed for the effect size explorer. You provide a little bit of information about what sort of study you're running, what sort of phenomena you're looking at, what sort of inferential procedure you're using. You just point and click, no need to upload anything, actually. And then it will dig through the data that we've already used to estimate error rates. And it will show you what sort of power, like how many subjects you need to be adequately powered at whatever power level you specify for that procedure. There is a big con. I sort of touched upon the idea that there is a big con here when I was talking about pilot data. And the con is that the generalizability of these results is limited to the studies that exist in the database. So if we, for instance, have no younger samples in this database, we might have limited generalizability to the younger samples. So as this grows, as this resource grows, it'll become more and more generalizable to a range of different contexts. And then part of the plan for this is to use some meta-analytic procedures to try to estimate, okay, we have some data sets from this population are using this set of scan parameters, this set of sequences, and some data from, other parts of the universe of possible measurements. What might it look like if this data was collected, using some of these sort of parameters, and try to just create some of those estimates to help tailor things a little bit more to specific use cases. So that's an ongoing plan. And I just wanted to give a quick little peek here and a little shout out that this is something that we're planning to not just be useful for power calculations, but other types of study planning. So I was saying earlier, for example, you could plan to collect a study that's going to yield a certain level of accuracy. Let's say you just said, I want my confidence intervals to be this big. How many subjects would I need to collect for that? That sort of thing. That doesn't have to do anything with null hypothesis statistical testing. You could use maps like this as a prior for some sort of Bayesian inferential procedure you want to use. Shout out to Mandy Mejia, who's introducing a lot of those really cool procedures into this world. But yeah, Daniel Lawkins talks about a number of different alternatives to typical power analysis procedures. If you want to check that out. So kind of a springboard for lots of stuff. So quick summary is that I would say, based on the data we have, it would be helpful to plan for considerably smaller effects for between subject designs compared to within subject designs, which matches some intuition. We know that's true, but it's also helpful to pragmatically and empirically estimate, how exactly these effect sizes compare. And demographic and biometric variables tend to yield much higher effects than psychological variables, which makes sense. Psychological stuff is very complex. It's implemented in a widespread fashion across the brain. It would make sense that would be very hard to detect. I'd say large open data sets and empirical benchmarking techniques are increasingly leading us to some really helpful practical guidelines. Seeing a lot of different papers across the field that's increasingly using procedures like this. Famously, the Eklund and colleagues cluster failure paper, I think sort of spurred a line of research that went much farther in that area of using large publicly available data sets. I think, it's a starting place. It gives us at least, maybe not the full answer, but more of an answer than just saying, I'm going to choose 25 subjects because question. And it helps us understand the practical consequences of what we need to do. I didn't talk as much about this, but some previous work, we show that you can actually get higher power when you use broader scale or multivariate inferential procedures. And that's one way to also, use your inferential procedure to improve power. And please check out this app and stay tuned for the ability to contribute to this. So that's all on the brain effect size. Let's say you went ahead and you did a power analysis and you went ahead and collected some data. So now we're at the next step in our research pipeline. It's time to do some analysis. So here I'd like to introduce a really cool suite of tools called Bioimage Suite Web. The lead developers of this project, Dustin Chinos, who is my postdoc advisor and is really awesome. Dino Papadimitris is also really fantastic. They've led this whole really exciting initiative that I feel like everybody should know about because it's really cool. And I'd love to see more analysis procedures in the field adopting some of this philosophy. And I also want to give a shout out to Javid, Zach, Cheryl, and Haley, not Hallie, and John, who are really important in leading this this development of this app. So BISWeb, kind of quick overview is that this is a web-based app. It's very easy to use, but at the same time, it's very powerful, which is an ethos that I've kind of tried to adopt in my own lab. There's no installation of anything necessary. You just go to the web and you use this powerful app. There are actually no servers involved. All processing that happens locally on your own computer. And this involves a very novel architecture to be able to take really powerful image analysis and processing procedures and make it accessible on the web and let it happen all locally on your computer. So you can actually disconnect from the internet and run some of these things once the app is loaded. So let's dig in a bit. I'll say there's an intro video. Yeah, let's do a quick look. I'm just going to check the time. Yep. Excellent.
For what you love. You can now, all in one app, add your calendars, work and personal.
I'm
add
very
your
confused if
tasks,
this is going to
have
be
your
a
tasks
3-minute long
intelligently
ad.
moved around events. This means no more draining daily planning, no juggling multiple
Let's
apps, and no worrying over what to do
this
next. Let its automated AI scheduling do the heavy lifting for you so you can crush your goals without constant reshuffling.
All right, there we go.
Users quickly
Welcome to BioImage Suite. BioImage Suite consists of a collection of applications which is likely to grow over time. The list can be accessed under the Applications menu in the upper left side of the page. The orthogonal viewer shows a 3-orientation view of images as well as an overlay. Several image processing and segmentation tools are available to alter images. The connectivity viewer will load matrices from parcellations and show a 2D semicircle representation of a 3D brain view of the edges and nodes. The MNI to TAL is an application map to load MNI to TALRAC coordinates and vice versa. You can drag the mouse to certain brain areas, show the Brodmann areas, enter coordinates by hand, or choose the Brodmann area to view. The image editor is an application that can be used for interactive segmentation and VOI analysis of images. The overlay viewer is an application optimized for displaying functional overlays in the 3-slice orientation view or mosaic tiled view of one orientation. The user can manipulate the threshold and cluster values in either view. The dual viewer tool is an advanced viewer application intended for image registration tasks. In one of the applications, you can click on the brain in the upper left and return to the original page. Under the Downloads tab, you can download a desktop version of the software if you prefer it, as well as a link to the legacy BioImage Suite webpage. The Documentation tab includes the user manual, a presentation about how the applications were coded, as well as the developer documentation.
All right, so that was an overview from Haley, who has since moved on. It's been a little bit of a while. All right. So we can start, I'm going to move the Zoom stuff to the bottom here. But if you'd like to follow along in the app, feel free to scan this QR code and we're going to do some kind of live point and click. Let me just go back. Here we go. All right. Oop, let me put the QR code so you guys can all. All right, let me know if you need that bigger to be able to scan. Otherwise, you can just search this web Yale.
There's a link in the slide.
Thank you, appreciate it. All right, here we go. There's the web app. All right, so we're going to start by launching the overlay viewer. That's one here. And this is kind of the most popular use of our tool so far. There's a lot of really great image processing functionality in here, but I think the most common usage has been to make visualizations, both connectivity visualizations and slice visualizations. And it's quite powerful and immediately useful for that reason, for that purpose, for reasons that I will show you guys in just a minute. So here we have an overlay viewer. You can easily just load some images and overlay data. For the demo, you can just go ahead to a help and load sample data. And here you go. This is the same thing as if you went file, load image, and you loaded, let's say this MNI structural image, and then you clicked overlay, load overlay, and that might be a statistical map that you want on top of that image. So here we are. You can play around with some of the different viewer controls. You can change, let's say, the colors. Save the overlay. Maybe we want different color schemes. Maybe we want it all red. It's very aggressive. You might want to look at different slices. So let's take a look at the different modes here. Oh, sagittal slices. That's in the orthogonal viewer. The mosaic viewer lets you have a number of different slices simultaneously. So let's say we want, 4 columns and 2 rows. And I want the increment to be every 5 slices, say every 2 slices. And we'll start the first slice about here. Maybe that doesn't show enough of the brain. We want 6 slices. And here we go. And you can take a snapshot on a white background and on a black background, and you'll have a nice, figure ready figure. Okay. You can also remove the labels for a cleaner figure, like that. So that's kind of like a sort of quick and dirty. You can just drag your images in and you can have a nice viewer. I think something that's really kind of cool about this is that it lets you create something called live figures. So this saves the full state of the application and the data that you put into it. So let's say that I am really interested in creating some figures that look like this. I'm not really sure, and I want to send it to my PI. And I want them to see exactly this view that I see. And I want them to also maybe adjust it themselves if they want to. So here we've, already loaded some data. Let's say share, collaborate, and you could also put this in a publication. Anyways, so we've already loaded some data. Now what you do is you go to File and you save the application state. All right. Excellent. So here we have the application state here. So if I, somehow lost this, oh no, I completely exited out. And I just take this application state and I drag and drop it here. It has the exact same view with the exact same parameters that I entered on the side here, the exact same data. So you can really quickly just send this file or put it on, a drive to your, whatever is easy for you, because it's a quite lightweight file. And then your collaborators can actively kind of help you find a perfect view or do some other interesting things, color palette, etc. So that's the live figures. All right, we can go to a cluster reporter. So again, we have this data that we previously loaded over here. And now we can go to overlay. No. Here we go, overlay color mapping. And then we can look at different clusters, threshold this image by different cluster sizes. So you can see as we have larger cluster sizes, the smaller clusters increasingly disappear until we just have a few clusters. So let's say we want cluster size of 130 or greater. And now we can get a little bit more info from this. So if you go edit, go to the cluster info tool, you're going to have to do this one more time for it to update. So let's say we wanted 135, 130, I'll put it there. So now you have the peaks of each cluster and a little report of every single cluster that's here for you. And you can click on the different peaks and see where each of those clusters live. It's pretty cool. And you can also export this table if that's something that is interesting to you. All right, so that is the cluster reporter. So we can dig also into some of the more heavy-duty image processing capabilities. Actually, we'll do something a little bit lighter, some smoothing. But in this suite, there is a number of more heavy-duty image processing capabilities. So I'm going to go back to applications. The ortho viewer. Yes. All right. All right. And so for this, we're just going to load the MNI T1, just the 1 millimeter RAS. All right. So we can do a bunch of different image processing things. We can combine images, we can smooth, we can temporal filter, some really simple things like reorientation might also be helpful for people, cropping, really, really basic stuff, and some other really interesting things. So here we're just going to go ahead and smooth this image. Here we go. First thing here. As an aside, we were working with AFNI a little bit over the pandemic to integrate one of their smoothing functions as kind of a test that we might be able to integrate some other of their stuff into something like this. I still think that would be fabulously incredible to have that whole suite of tools that they have here. One day we just have to make time to return to that, because I loved the idea of having, you know, point and click all of this complex fMRI processing stuff in the browser. All right, so we went to image processing, we went to smoothing. You saw on the side here that smooth image popped up. Let's do this. All right, so we're going to choose a smoothing sigma. Let's say, I'll do 3 millimeters. And then we just go ahead and click smooth, which is down here being hidden. And there we go, really quickly just applied some smoothing, Gaussian filtering. And then you can save this new image if you're interested. I'll just save this one. Cool. All right, and here's another image processing procedure. We can combine some different images. Here we go. So let me load. We already loaded the T1, and as an overlay, I'm going to load that smooth image that I just created. Oh, load. Yep, I click save. All right. Here we go. That's the smooth one. And I'll load the normal MNI that has not been smoothed. And we have the overlay already preloaded. So for instance, something that we could do is we could subtract these two things together. I'm going to go to here and combine images, exit on the smooth. We can click Operation Subtract. Image 1 is the image. Image 2 is the overlay image that I loaded, just that second image. And we can execute just a subtraction of those two things. And we can see the areas where the smooth image was different from the original image in purple here. So of course, as we smooth, we increase the boundary of some of these voxels that are ordinarily not even existing in the original unsmooth image. So very quick things like that. See, we also have a defacer that we actually had a little hackathon back in 2018 to create this defacer, and it's just going to do normal kind of registration to an MNI that also has a defaced mask to that. So if you need something defaced really quick, image processing or segmentation actually is where that one is, and defaced head image, and you can go ahead and execute that as well. And there's a video. Just for the sake of time, I think I won't go through that one here. There's a lot of videos under that documentation side, so feel free to check out the YouTube, also extensively documented in text format as well online. All right, so let's also take a look at the dual viewer. Let's go back to the original suite tools. Go applications, look at the orthogonal viewer tool. And here we'll just load some MNI data. Oh, I clicked the orthogonal. Sorry, I meant to click the dual viewer. And it says this here too, orthogonal, but you'll want to click dual viewer. All right, so I'll just load an MNI here, and maybe I'll load another MNI here. We actually don't have a full tutorial for this planned out, but I just want to show you here, you could do things, you know, linear registration, nonlinear registration. And it's kind of interesting. You can run something like nonlinear registration in your browser, runs about 90% of the speed as if you just had it, you know, locally installed, which is pretty cool. But I won't do it now because even fast nonlinear registration can be slow. All right, and we also have this connectivity viewer, and we will go through a bit of a tutorial for this one. So we go back to Bioimage Suite Web Tools, and we're going to launch the connectivity viewer. We also have a mouse connectivity viewer and a lot of things we were interested in doing. If any of you are excited to do any development on BISWeb, we would very much welcome that. So there's a lot of cool directions we can go in. And the mouse viewer is one of the cool new directions we've gone in. There we go. So here's a connectivity viewer. We have the circle map here, we have the 3D brain here, and kind of a map of the atlas down here using the Shine Atlas and with some of our network definitions. So for this, we're just going to load some sample matrices. So go to help, then load sample matrices. And as you click around, you can see all the, so here are the sample matrices that were loaded. This is just a, let's say if you imported a text file with just a binary of ones where all the positive connections are and zeros where all the negative connections are, or zeros where where there are not positive connections, and then a separate negative matrix where there are ones where there are negative connections, then it will take these matrices and make it into these plots. So if you click around, this is for each node, you can see all the other nodes that it's connected with. So you could look at individual nodes, you could look at networks. What is prefrontal cortex connected with? Temporal cortex. You could look at the whole thing. It tends to be overwhelming. Often in analyses from machine learning analyses and differential analyses will have large widespread effects. Again, there's a lot of this evidence that many types of effects that people care about in the brain are indeed widespread. So it's helpful to think about these large networks and how to do some summaries of them. I'm going to sort of circle this brain, see how densely interconnected the brain is, which is probably pretty good. All right. And we can go from, this fully densely connected matrix and say, well, we need to summarize this a bit more. Let's make a chord plot. This kind of shows you what each network is connected to with kind of a subdivision based on, one thick line based on connectivity from cerebellum to whatever this is. Maybe it's some subcortical thing, limbic network to, let's say, visual. And of course, you can save all this stuff, create summary matrices, just counting the number of connections between things. We have a developmental form of this, which is normalized by the total number of edges, which you should always do between networks. So if there's one pair of networks that has 100 possible edges between them and another pair of networks that have one possible edge between them, you're much more likely to be able to observe just by chance, the network that has 100 possible edges, seeing at least one there versus one in the network that only has one possible edge. You have more shots. All right, so you can do saving, you can sort of visualize all this stuff, you can create a snapshot of all these different views if you wanted to. You could take a panorama, that's just a snapshot. You can do panorama, which gets all the different views. We use this a lot for papers. I think the connectivity viewer is perhaps even more widely used than the orthogonal viewer for visualizations in papers these days. All right, cool. So something that I think is really great about Xenios and Dustin is that they come from a really nice, rigorous software development background, in addition to being really focused on applications. Like Dustin is very interested in developmental applications, and he's kind of this brilliant person in all those different contexts. They're very interested in making sure that, of course, we're going to be rapidly developing software like this. We want to create regression tests to make sure anytime there's an update to the software, it's behaving in many different ways that you would want it to. You would want it to behave in this updated version, just as it did in the previous version, in very specific, well-defined ways. So they've developed a number of regression tests to make sure that each update is actually consistent with the previous performance. So we can go back here. Yep, here we are in the main app. Go to developer info. Just move this out of the way. And down here to run regression tests, we can do, let's say, just the display regression tests for now. So for now, we can run just a single test. So this is the gold standard that it's expecting. This is the actual result, and it reports whether or not, it passed this gold standard. You can run multiple. There's an intentional fail built in there. Like if something is supposed to fail, then it passes. But it goes through all these different tests. And I think that's great because you never know whether one small thing might cause kind of an avalanche that changes one unexpected downstream behavior of the software. And you can also do regression tests for specific modules. We go back here, just sort of kill that. And you just select a specific module that you'd like to do the regression test for. Smoothing the image. So it's going through and running these tests as well. So you can kind of zoom into specific modules that you've been interested in. All right. So I've talked a lot about kind of like the hands-on operation of this software. Let's talk a little bit about the architecture of the software. So the kind of heart and soul of this is built in C++. That's how we get these algorithms that run so quickly. And then it gets compiled to either WebAssembly or a native shared library. Those of you who might be interested in web-based development, feel free to chat with me a little bit more about that. And probably I will point you towards Dustin and Xenios as necessary. But for now, I'm just going to kind of quickly go through some of these things. A big thing to note about WebAssembly is that it basically makes C++ usable in the browser. And compared with native C++, if you're using JavaScript, you would get 50% that speed compared to native C++. If you use WebAssembly to do that compilation, you would get 90% of the speed that you would have with like a natively installed C++ application. So we also have some JavaScript modules here and ways of sort of making it so you can access this compiled C++ web app from JavaScript or from MATLAB or Python. And I just want to emphasize, you don't have to install anything. There are no servers involved. It's just all readily available to you once you've launched the app or once you have access to the code that we've created that has been compiled to WebAssembly. And then next, I'll show you kind of like an example of why this is so nice. There's an individualized parcellation module that was created for Marave's project. Merave Salehi was part of Todd Constable's lab, whose lab I was part of during my PhD. And you can actually call this module that was originally built in C++ from JavaScript like this. You specify some parameters. And then, oh, whoops, just at the beginning there, you specify some parameters and then you pass into the actual function, which is this BISWrap individualized parcellation WebAssembly function right here. You pass fMRI data, some group information, those parameters that you've defined earlier. And, if you have some debugging parameters, and it will just go ahead and run this through JavaScript. Or you could run, this module through Python. Again, define some parameters up there, then pass that in along with the fMRI data and the group information. Or through MATLAB, again, define some parameters. And we see that function again, a little basically a wrapper based on the WebAssembly version of this parcellation code, where you provide the fMRI data and the resliced group information and some parameters. But this is kind of really interesting. And I think it's something that's very wise of Xenios and Dustin to think about how we could create kind of a centralized, very intensive image processing algorithm in C++ that could run very fast and then could be accessible in any sort of language that someone might be interested in. And I'll definitely, we've been wanting to publish something about this for a while. And if you're interested in this, I definitely would point you, I'd be happy to chat, but then again, point you towards Dustin and Xenios, who are the brilliant minds behind trying to think really carefully about this architecture, making it not just very usable, but accessible from different types of environments that people might want to work with, and then making it just a very low burden on the part of the user. There are also a few different command line tools that you can use to access this functionality of BISWeb. So if you're familiar with Node.js, you could use Node to install BISWeb tools after installing Node, of course. But it's as simple as, often, it's hard to say everything is just as simple because often people run into bugs, but it tends to be pretty straightforward. Download Node.js, install, and then just npm install BISWeb node. And then you can do any sort of like BISWeb node smooth image -h, and that will do your smoothing with any sort of additional parameters that you might want to provide, or run the regression tests just, at the command line. So, we have You can access these tools from the web. You can access these tools from the command line. You can access these tools from MATLAB, from Python, from JavaScript, lots of different contexts, whatever is interesting to you. So I said this before, and I want to say it again. If you're excited about BISWeb, if you have more of a computer science background, or if you want to have more of a computer science background, or familiarize yourself with web development, we have been really excited about contributions for a while. There's been a lot of momentum in the early days. It's slowed a little bit, but I think there's so much potential in this application. It's still very much being used, particularly for the visualization context. And I just see there's such potential to create a bunch of tools that we would use, and perhaps just somebody with command line expertise or bash programming expertise would be able to use, but instead make all that accessible in the browser in kind of a point and click fashion. So please feel free to let me know if you're interested in contributing. We also have a number of resources. If you look at the documentation tab, YouTube tutorial, user documents, documentation, developer documentation, depending on where you're coming from and what you want to do. And the main repository lives here on our GitHub. So at this point, I would just like to thank so many people. For the first part of this talk, we talked a lot about brain effects, and my lab has been really awesome in helping the development of that. And we've been doing a lot of really exciting work on the reliability front as well. So awesome work by Alex and Hallie. Please keep an eye out for them. Then there's the BISWeb team led by Xenios and Dustin at Yale, and also the Minds Lab with Dustin at Yale. The Minds Lab has been really instrumental in helping contribute some of these really interesting data sets for the effect size project. And a number of other people have contributed to various projects here or indirectly to related things that I've been thinking about and ways that I might build on these projects. My funding sources, the amazing publicly available data sets that without which we would have we wouldn't just have these tools missing, but we would have a number of other tools in the larger ecosystem in neuroimaging that are essential for us to be able to do the work that many of us can do today. So with that, I'd like to thank you all so much for your attention and just open up the floor to any questions that you might have. Thanks. Yeah.
This is really cool. I've been kind of eagerly awaiting all of the tools I used to look at the website. And I saw you have developed documentation. Do you have a system for writing plugins by any chance, or have you thought about some way to write plugins?
Not at the moment, unfortunately.
I imagine that's hard. It's C++. That's what's getting clouded.
That would be, yeah, absolutely fascinating. We should definitely keep in touch. Any, I think, enthusiasm about where to take this, I think would be phenomenal. Thank you for asking. Yeah. Yeah,
that's super cool. One big question. There's a big movement in life, like they're doing a fantastic job in terms of the is there any possible connection? I don't know how their code is and like embedded in that apps, but I'm just thinking like utilization in that in the community is not like it's a huge if the community manages to kind of converge in one ecosystem, that might be super useful, especially for the contribution aspect. And a lot of what we're doing is about utilization. I think if you have every computation aspect, probably it's something that's important. So do you have any thought on how to connect possibly those two projects, or maybe some general code on the
yeah, that's really great. And I see also a number of different communities or labs building one-off visualizations as well. And it feels like, yeah, if we all sort of combine resources and combine our thoughts and our philosophy on how to do some of these things.
Like a nice people, but no policy edition.
Yeah, exactly.
This it's kind of okay. Yes. things that got on one system. I think that whether something and browser aspect is a big branch. I'm just curious what. You know,
Yeah, I think that that would be extremely important. I'll be realistic about, for BISWeb, there was funding for a while to sort of keep the project actively developing and moving forward. And there's always been so much enthusiasm about BISWeb, but there hasn't been as much of the ability to focus funds and resources and time. This is, an age-old story for all the developers in the community. You now have this other project and you have to manage that, and it's just hard to like keep the momentum here. I feel like if we came together, people who are developing a lot of these tools, and we purposefully, decided to collaborate. It's interesting because we were talking about, effects, and we were talking about Neurovagal and Neuropoppy and how we could all be working together as well. And there are a number of these instances where if we had spaces to sort of all talk about these shared goals rather than creating these one-off things that are so hard for one lab to maintain itself.
It is super hard, and actually in academia, it's super hard to do this sort of thing because often there's one lab that is leading and that has like this recognition aspect and ranking aspect.
Yeah.
But I know those projects that are multi-labs, often taking the example of bits is obviously one thing, like it's really community driven. Neither it is another kind of package or DiFi or there's a number of packages that are multi-labs. They're more resilient.
Yeah.
And the more that they sometimes when the lab will have some funding and we get going and it's another one like that's like multi-lab aspect is very important for this kind of product because we can't maintain all those things.
I know, yeah.
And there's always new things. So maybe moving this further, but more like longer, like more slowly, time. I don't know, it's a general thoughts. Sorry.
Yeah. No, I love it. And I really appreciate you bringing that up because it makes me think one of the most important things for the longevity of BISWeb, and I think the utility of this really cool philosophy that they've thought really carefully about this structure and have had really great software development sort of expertise. One of the best things for the longevity of BISWeb and to keep all those ideas going and shared with the community is to think about how other people have managed to bring this to like a multi-lab collaboration, which is something I'll have to talk with you guys, you three, about and learn more. Because this really has been a single lab, like really exciting push. But unfortunately, one lab can't do it all, as you're saying. Absolutely. So thank you. Yeah. And there questions? It can be about development, it can be about effect sizes, it can be about study planning, power analyses, alternatives to power analyses, empirical benchmarking.
That's
Yeah, not power analysis. Yeah, of course.
Thanks. I'm so excited about all of these tools. And really appreciate hearing about them. I have a question about that I think I probably won't have any information about, but I think that's a brief question. How do you maybe foresee, and maybe something that is already happening, but foresee the tool potentially being used for multivariate models? It's something that I'm really curious about, is this idea of potentially using fMRI to better, but also in multiple subgroups. And I'm curious, given that I think the fact that there potentially would be a lot of subgroups to that kind of variable, it would make it sample size a little bit trickier. You would need a large enough sample size. Anyway, long-winded way of asking, like, I guess how you would see the tool as potentially being able to accommodate, I guess, like, yeah,
Yeah, it's a good. Oh, yes. So we were asked how the tool might be used to, the brain effects tool and power calculator could be used to accommodate study planning for latent variable analyses. It's a good question. So it's interesting because we're talking about things in the context of standard, linear models for right now, just one, let's say, linear model, even if it's a complex inferential procedure built on that linear model. And then, kind of a natural offshoot from that is borrowing from some of the power estimation procedures for things like multi-level modeling, mixed text modeling kinds of stuff. And there are a number of guides for that. When we go further and further from that, things like latent variable modeling, structural equation modeling types of stuff, which have their own unique ecosystem of very idiosyncratic power estimation procedures. It's a little bit different from what I've currently been thinking about, but I do think that anywhere that you would be able to do some resampling, or let's say if you can do a permutation test to do some estimation of p-values, you should also be able to do some of this resampling to estimate some of the other errors that we're interested in here. That said, I am not an expert in structural equation modeling or latent variable modeling. I do have a very close collaborator who is an expert in those things. So if there is interest in that particular domain, I think it'd be really interesting to go in those areas. And I think that's also kind of a theme of this is power calculator for standard inferential procedures is kind of like the very most obvious thing that will be useful to a lot of people. And then there are many different directions we can go from there. And this can lead to development of a lot of different new methodological procedures. So I envision, either having this be usable to other people to develop their own procedures, or if there's enough demand in a certain area and say we've got funding for that area, we would rely on people in the audience to sort of contribute and let us know what that demand is. And as JV was saying, something like this, I think like all of these small software tools, it's if you want it to be a community-based thing, it has to be something where there's more community involvement and development and not just the purview of one lab. So I think thinking really carefully about that, I do want it to expand. So we would have to be really intentional about building community. And I'm still thinking about that. Step one, I think, is, giving talks like this and raising awareness and just seeing organically who might be interested. The step two, I think, is like engaging a little bit more with specific people who have specific development expertise and are interested in using products like this. Thanks. Yeah.
So I guess it sounds like what you're saying is that, if this was a potential interest from a large enough subset of people, that maybe that would be some useful. I'm curious generally, this might be a very simple question, but how typically that type of interest is started?
Oh yeah, that's a very good question. That sounds like in the purview. Yeah, JV, you may know more than me. Actually, all three of you. But yeah, it sounds like the sort of thing that someone like FSL or AFNI or a really big software project would have better understanding of how that gets surveyed. I think you see that there's usage in certain areas, like somebody might use a certain, let's say, power estimation procedure, but it's very suboptimal. And then you see many people in the community use that estimation procedure. And then maybe you show how it's suboptimal and you show that there's another alternative. That's one way. You just see how there are gaps in what people are using. I don't know if there are often formalized assessment of users to try to see if there's gaps that they specifically. Yeah.
First of all, how many factors are using some without sample size and the survey research
Yeah.
Make but in general, no one do that. That's the problem. That's
Absolutely. Yeah, I think there are other strategies that are suboptimal, like directly assessing the user base. Like a million different people are going to complain about a million different things, which is something that we see with BISWeb. But there are, actively used forums where you might see some consensus about what people are asking for. Maybe these days you see people might submit an issue on GitHub and say this is a need, and maybe a lot of other people see it, but I don't know how. I'm not sure. In my experience, we see that being a big driver of like the major parts of change in software development. They see from that. Thanks, Noah. Good question.
Question. Moss says, good stuff. Have you looked into effect size differences across ROIs and do the effect size distribution support RFT?
Support random field theory, RFTE.
RFT.
Yeah. So whether two different questions, which are both really great questions. One is there's definitely marked differences spatially across different ROIs and across different edges in the connectome as well. So both in the task-based context and in the functional connectivity context, you tend to see certain, at least in functional connectivity, you tend to see certain subnetworks that have stronger effects than other subnetworks. And typically, we see within network effects being larger than between network effects, which actually we tend to see test for test reliability is also larger within network effects as well. So, but there's definitely variability in that respect, spatially, and you can look on the Effect Size Explorer to explore that more as well. Whether it supports random field theory, I think that if we go back to, the Eklund paper that talked about some of the assumptions of random field theory that are sometimes don't quite hold when you set certain parameters, for instance, when you're doing your analyses. I think it's not necessarily something that we have been looking into specifically in the effect size project, or whether those assumptions all hold. But I think that there have been a number of people that have been looking at whether the spatial distribution of effects support random field theory based inference. And I would start with the Eklund paper and kind of go through there and sort of learn about what those assumptions are. Because unfortunately we're not answering it, but it would be interesting to use some of the effect maps to see if you can test certain assumptions of different inferential procedures. Thank you. Great question. Yeah, sure.
Yeah, thank you for the talk. Super interesting, different products. I was wondering, sorry, I just missed it. You mentioned that brain effects will like procedures. I'm thinking I'm working on my first RSA study, which for the analysis. So how would that actually work? Could you elaborate a bit on that? Like, how would you get that stuff for non-measured sort of power estimates for the procedure that is presumably maybe not
Yeah. When I think of representational similarity analysis, I'm thinking usually of things that are a bit outside of the context of conventional inferential statistics, but I'm not as familiar with representational similarity analysis we should definitely talk about it, because the idea is, the procedure that we're using for benchmarking power for cluster-based inference, the idea is you have, the full data set. Let's say you have 1,000 subjects, and you look at what the effect looks like in that full data set. And then you should be able to define what the positive looks like. For something like a multivariate procedure, a positive, any effect is basically if it's non-zero, and it's going to be non-zero because of sampling variability, there's going to be an effect. So then you say, for let's say a different multivariate procedure that maybe I would be more familiar with, you would say, how often do I detect any effect at all? And again, that's probably going to be something that you would detect every time. And that's where I think standard, inferential statistics, I think it doesn't apply as much, or it shouldn't apply as much, because you're always going to detect something. So how could you define whether something is a false positive? You would need to be able to define both what a false positive would be and what a true positive would be. And if they're all true positives, then you could use any procedure and just say detect an effect, So there's that thought. I think for multivariate procedures, and we've been starting to try to think carefully about this. It can be a little bit more maybe helpful to see, whether the multivariate effect is in the direction, let's say an n-dimensional vector space, in the direction of the actual ground truth effect, or how far is that vector from, a true, the true ground truth vector. for example. But yeah, I think it's a little bit, it's more yeah, multivariate inference, I think it's a little bit more complicated when it comes to trying to think about true positives and false positives. It's a great question. We can talk more about that because I am also personally very interested in going down the multivariate space. Yeah.
Just kind of one quick thought, because every time I hear that the Econ paper is pointing to problem hypothesis of the RFT, of the random filtering, it is true that there is some hypothesis and it's an approximation, but the main effect of that paper was the setting of the threshold. There's a threshold where you set for how where you got to make to create those clusters that we're going to look at the standard. Okay. That's the main effect. Like, the RFT is not very precise. We may get 7, 8, maybe 10% max. So the post positive but if you have a high threshold, it is going to be a reasonable approximation.
Yeah.
It's not going to be 50%. The paper doesn't portray that very well. And at the time, it's because, and for the backstory, for those interested, like the SDA, that's by default high threshold of 1, 0.01, and FSA has a low threshold. And then if you want to portray the paper and okay, we have a bad default threshold in FSA. So anyways, what I'm saying is that yes, obviously that it's just an approximation. I mean, you can be careful. Don't believe in that 5%. But in general, you're doing well. It's just like you have to set that threshold sufficiently high.
Yeah, I completely agree. And I'd say that there are a couple other things that are worth considering even more than the fact that if you set the right threshold, technically random field theory, you've kind of satisfied enough of the other assumptions for you to get somewhat valid results. One is that there's non-uniform spatial smoothness across the brain, meaning that in some areas that are just intrinsically smoother, you can be more likely to see a false positive by chance. Because if this whole
It has been solved.
It's topographic. That's true. Yeah, I think it's not as commonly used, but yeah, I think that's like when we're talking about like standard historical uses of the software, people tend to have overlooked that. And I think that's a big one. And then, so there's that, the fact that there's non-uniform smoothness and people should be respecting that. And they can, but they just often we don't. And then there's also the point that I didn't get into this time, but which has motivated quite a bit of my work, which shows that we tend to see that effects, when we look at these larger data sets, we tend to see that effects are often widespread across the brain in task-based activation context or across the connectome in functional connectivity. So why would you look for small focal effects if the true effects are very widespread? We take advantage of local dependence. If this voxel is activated, probably the one next to it might be activated. But we don't think about the fact that there are, widespread networks across the brain that are not necessarily spatially adjacent to one another, but they are functionally adjacent to one another. So I think being a little bit more thoughtful about doing inference at the level of these widespread effects that are really well known to be dependent. We always see these widespread resting state networks. We see them again and again. They're not always the exact same areas, but we can pretty reproducibly find, a default mode network in a lot of people by seeding, a seed in the PCC. We see these widespread networks all the time. So why would we expect, focal effects all the time? And I think this is another thing we're going to be able to take advantage of more and more when we have these larger data sets, so we can understand a little bit better the large distributed nature of the true signal. So, I think I wrote a paper recently about this that's more kind of philosophically oriented. It's about the tip of the iceberg, some of the pitfalls of looking for very focal effects when you're looking at complex cognitive processes or psychological processes or clinical processes like psychiatric disorder. So if people are interested in that, I'd encourage you to take a look at that.
Okay, thanks everyone. Let's take Stephanie in.